Monthly space news, we do this every month corresponding with our meetings. First thing, good news is the U.S. is back on the moon. We had been away from it for a while. Yeah, actually, almost 52 years in December to be 52 years. We hadn't been there. A long time ago, we'd landed some stuff, some robotic kind of stuff. Of course, we sent astronauts there, and now finally we were going back. Taking a long time. The one that made it is called Odysseus. That's the name of the mission. The company that actually sent it is Intuitive Machines. The type of lander is called Nova C, and I'll just refer to it that way because it's shorter. They took off on a Falcon 9 rocket on February 15th. It was launched. They took a very direct path, pretty much the same as the Apollo astronauts took to get to the moon, and landed there a week later on February 22nd. And as we said, that's the first landing, first soft landing. We've had a few others. One was actually deliberate, where they wanted to see ice get thrown out when you crashed into the south pole of the moon. But basically, this is the first serious landing in a long time. There were some other firsts associated with this. It was the first successful moon landing by a commercial organization. Now, there had been several. There was a Japanese one earlier, and also Astrobotics, a U.S. one, which also had failed. The U.S. ones are all part of a program called CLPS, which stands for Commercial Lunar Payload Services. And the idea on this, it was really kind of revolutionary at the time, was NASA would buy services, pretty much like buying UPS, or FedEx or something. You're a trucking service, and you're going to get stuff to the moon. It used to be that NASA would always buy everything. They'd make a lot of individual missions, one at a time. They'd all cost billions of dollars, and they wanted to do something different. And the thing is, these are all unmanned, so they can be much riskier. And that was a big part of this whole program is, let's try some new stuff. Let's not just keep using the same old engines and the same old techniques. Let's see what we can do. And bring in the private industry. So this whole mission cost about $130 million. Now, it is considered a private mission. Now, the reality is the main customer of that is NASA, because they had a lot of things they wanted to find out. We're sending people to the moon, but we're sending them to the South Pole area where we've never been before. It's a lot rougher. We want to find out more about that area. So there's a good reason why you really want to send some probes ahead of time and learn more about that area. So anyway, NASA total delivery contract service was about 118 out of the 130 million total. The rest was made up by investment and by some other commercial customers. And that's one thing about these missions is they're allowed to have commercial customers, and there were a few. The big thing about this one is it was the closest ever to the South Pole, the lunar South Pole. And that's important because, as I said, the Artemis program, which is the U.S. manned space program, will be landing astronauts there. So we wanted to get more information about it. We've never landed that close to the South Pole before. And particularly, they're going to do things like scout for the presence of water ice. The South Pole is really a very strategic place, South Pole of the moon. A couple of reasons. One is we know there's water ice there. And once you have ice, and besides being able to drink it, you can use electrolysis. You can generate oxygen for breathing. You can generate rocket fuel. There's a lot of things you can do with that. But you got chemistry you can work with. And that makes it very strategic because it looks like it's going to be pretty easy to get there. There may be some other places, but down in deep craters at the South Pole in particular, in the shade when the sun never hits, it looks like there's a lot of water there. And the other reason why it's so strategic is that at the South Pole or very close to it, if you put your solar panels up on poles, you can get sun pretty much 24 hours a day, or at least close to it. You can't do that anywhere else on the moon because the moon itself will block it, just like day and night on Earth. No difference there. So that is very strategic because it's easier to get energy there. Longer term, we're going to end up with nuclear energy one way or the other on the moon. But for a while, you're going to at least want to have a lot of solar power. So that's why it's so strategic. And in fact, everybody's going there. There is really a space race going on, and it hasn't been that apparent until now. This year and last year, all of a sudden, you're seeing a lot of people sending probes. Not all of them has succeeded, but they're going to be succeeding more and more. And it's on. There's no question. Of course, the main competitor here is China. They are the other major space power. Russia is pretty much just kind of an add-on as far as they're concerned at this point. Okay, the lander itself is about 4 meters high, counting the landing legs and the solar cells up on top there, 2 meters wide. It weighs about 1,900 kilograms, basically a couple of tons. It's a car. 4 meters high, think of that as 12 feet, 2 6-foot people. It's that kind of a length. You can put 100 kilograms, 220 pounds, on the lunar surface. That's where the C in the name comes from, C being 100 in Roman numerals. And the interesting thing here is the payloads are all on the outside. What you see is pretty much what you get there. So looking at this thing, there's some solar cells on the top. There's 2 sets of solar panels that kind of go around the sides here. And so notice, of course, as I was saying, the higher up you get the solar panels, the more sunlight you get. And so that's a really good thing. And then anything going to the South Pole, they're really designing that way. There's 3 solar panel arrays total. 2 are visible here, one's on the other side. These things here are compressed helium tanks. That's used for controlling the orientation of the spacecraft. And everything else is inside, protected, except for the payloads, which are easy to attach. You just stick them on the outside and you're done. The solar cells, as I was mentioning, you have 3 sets of panels. We label them here. Still, you can't survive the lunar night in this thing. At least you can't plan on surviving it. Electronics, it gets very, very cold there. The night lasts 14 Earth days. The lunar day is 14, and a lunar night is 14 Earth nights. So you can't do that. You have a battery, and you can work out the math that it's worth maybe 3-4 hours at maximum power, comparable to what the solar cells could put out. Now, of course, if you know you're going into night, you would cut back on most non-essential stuff. So you could probably run 10-20 hours, but that's about it. Most of the power would have to go to heating it. So basically, people just give up.
200 watts of power, that's about like 3 old-style floors.
Yeah, oh yeah, yeah. You couldn't light this room with that. No, it's not a lot. Obviously, they're very energy efficient. Okay, this is the first lander that's using methalox. Now, that's just a short way of saying methane plus liquid oxygen are the main fuels. And that's quite different, especially for anything deep space or even counting the moon. That is getting much more popular with all rockets. For instance, the Starship coming from SpaceX is a methane rocket, as is the Blue Origin competitor when that comes along. This is kind of an exploded view of that lander. The methane and liquid oxygen tanks are inside. And of course, we showed the helium tanks. Traditionally, they use what are called hypergolic propellants. That just means by themselves, they don't do anything. But when they touch each other, they immediately essentially explode. They burst into flame. That's very useful for deep space missions where you might go for a long period of time with no engine running. And then all of a sudden, you got to do a maneuver. And so you know that you just put the fuels together and the engine lights up. And so the hypergolic fuels have been very, very popular, almost always used for those upper stages or the spacecraft that are going out, deep space especially. That's tradition. So they're also easy to store. They're liquid at both space conditions, so you don't need special, really exotic tanks and cooling and all that. On the other hand, it's very toxic. And it's very, very expensive and dangerous on Earth. And I've showed this picture before, but over there on the left-hand side, there's a guy dealing with this stuff, hazmat suit. And why does he need that? Well, it's flammable, it's corrosive, it's toxic, it's bad for your health, and it's bad for the environment. I mean, other than that, what's not to like? Yeah, those are the standard warnings that go with it. So it's the first one using that. Why do people want to use methane and liquid oxygen? Well, it's higher efficiency, for one thing. Especially, it's cheaper as well, especially on Earth. Methane fuel, basically, is pretty much what's in your natural gas. And it could be manufactured in space, which is part of the appeal as well. Mars in particular, you can manufacture it on Mars and other places. Now, generally, though, it does require cooling. That's more of a problem on Earth, so you have to have special cooling to keep it down at atmospheric pressure. It's like minus 260 degrees, so it's cold stuff. In space, ultimately, there's going to be some kind of pressure release. If the thing gets too warm, some will get released. The boiling of it, that carries the heat away. It's like a Dewar flask on Earth. In the case of the Nova C lander, they hope they don't even need to do that. And in fact, they didn't need to. What you do is you do what's called subcooling. Instead of just running it right at the boiling point, you load it much, much colder than that. And as a result, as the heat gradually leaks in from the atmosphere around you or space around you because of radiation, it warms up, but it doesn't really vaporize that much. That's the same trick that SpaceX is using on Starship, by the way. They try to subcool the liquid as much as possible. They don't keep it just at the boiling point. Now, SpaceX, given this is running on their older rocket, the Falcon 9, they didn't have methane there. So they had to modify the launch pad to handle that. They also had to change the fairing, which is what holds the payload in place. They had to change that so they can get methane in at the last minute. You don't want to keep it there too long. You're trying to get it subcooled right before takeoff. So you just load it the last couple hours at most, and then you take off. And anyway, so now they've actually run this, and they are now the first methalox engine that's ever been restarted out in space, anything beyond low Earth orbit, anyway. So they set some records on this. The payloads, there's a long list here, but they're all actually pretty useful things. This is not the basic science kind of stuff that you get in a lot of NASA projects. These are things that are going to be actually useful for going to the moon. Things like getting better estimates of the mass that are in your fuel tanks, which is extremely important because we're doing a lot of that. There's going to be propellant transfers while we're in orbit. And it's kind of hard in microgravity. Stuff just kind of floats around. You get little bubbles of stuff. It's not just like you just stick a little float in there. There's no gravity to pull the float down. and there's no gravity pulling the liquid down. It all just kind of disperses everywhere. You need different kinds of mass gauge. They were doing some testing for some navigation stuff. They were going to drop some navigation reference points to help improve navigation at the moon. The laser reflector is just basically a little thing that you just set on the ground. It allows you to send a laser at it and get reflections back to help identify where you are. Very, very passive, not much to it. But they also had some radio navigation beacons. The idea, kind of like GPS, except instead of the satellites overhead carrying the coordinates, pretty much they're just spots on the moon that'll be known. And then as you approach the moon, you can see the navigation spots, or you can pick up the radio signal from them and navigate based on that. They wanted to look at the dust that you throw up as you're landing. You're throwing up a heck of a lot of dust. And they really wanted to try to model that a lot better for designing how they land these things. And do we need to do special preparation of landing sites, that kind of thing. Some problems related to communicating. When you're near the South Pole, a lot of the time to communicate with Earth, you're pretty much sending a signal to the horizon. And when you do that, just like on Earth, actually, the radio waves tend to bounce off around the land and everything. You get multipath distortion. There's different kinds of problems you run into. So they're doing some testing to try to get better communications. And also radio astronomy. It turns out low frequency radio astronomy, you can't really do it in the Earth just because of the atmosphere or the ionosphere. And they think they can probably do something on the moon at different frequencies than they have before. So they're looking forward to that. And also, dust is levitated. There's a bunch of electrons just kind of floating around very close to the surface. That levitates dust, which it gets in the way of everything. It gums up your spacesuits and all that. So they had a lot of things that we're looking at. Commercial stuff, I'll skip over most of that. Interesting stuff, but we're a little short on time. Okay, let's get to the operation. They were launched on a Falcon 9, direct heading for the moon. What's called translunar injection, which is a standard orbit. It basically means going from Earth, sending it to a place where you can then orbit the moon. So it's the path between the Earth and the moon. That's called translunar injection. So they pretty much just went right to that. We've covered some of the previous landers that have gone up. Typically, they were up on rockets that were a lot less powerful. And they took months to get there. And they did these really roundabout, circuitous ways of getting there. But they were very low energy. They didn't need much fuel. The Indian one that went up fairly recently, they took 2-3 months. I forget what it was. It took forever. And the same went with the astrobotic one that was up there too. All of them, they took a long time. We had power to spare. The thing only weighs a couple of tons, which is really not that much. One Falcon 9 rocket can handle that. One sign of that is the booster. Normally the booster comes back to Earth when a Falcon 9 is launched. But the question is, where does it go? If you go in what's called expendable mode, where you just burn up all the fuel in the booster, obviously the rocket, second stage goes farther, and then the booster just falls into the sea and is wasted. If you use a little bit of fuel, you can return to a drone platform in the Atlantic Ocean from where they're launching. And that takes some fuel. You got to use up some fuel to do that. Or you can go all the way back to the launch site. And that's what they did here. So that's kind of an indication that they had power to spare, not a problem at all. So anyway, the flight to the moon, they establish an orbit, roughly circular orbit around the moon itself. And the reason they did that is this is really fully autonomous landing. They have to actually circle it multiple times. They have previous imagery from satellites that have been around the moon for a long time, but they were trying to pick an optimum spot to land. And so they make multiple passes to make sure they're there during the right lighting conditions and everything else. So they did that. They had 2 major failures, and those are procedural failures. These are not hardware problems. They have a laser rangefinder, which is needed for landing. As you're landing, you're coming down, you need to know how much power should you be sending to your engines. You need to know exactly where you are to do that well. And so they had a laser rangefinder as an altimeter for doing that. It failed, or what really happened was it just was never turned on. There was a manual switch set back before launch, basically just switching the thing off. It was a safety issue. That thing is not safe for eyes at all. It would definitely burn out your eyes if you looked into it. And they forgot to turn it on. And this is a physical override, not something you can just override electronically. So they forgot. Next time you can bet they're not going to miss this. If it was not on the checklist, it will be the next time for sure. Okay, that was the problem. But of course, nobody noticed it. The reason they noticed the problem was when they first established orbit around the moon, it wasn't really as circular as they wanted. They were a little uncomfortable. It was kind of elliptical. So they wanted to make a correction. So they figured, well, okay, let's turn on the rangefinder and let's calculate what we need to do to fix the orbit. Well, they turned it on early, and that's when they discovered it didn't work. And if they hadn't done that, they wouldn't have turned it on until about 5 minutes before it was used. Probably they were already starting, hitting down. That was kind of a bad design, a bad operations plan to begin with. It was just pure luck that they happened to notice it because of this, but they did notice it. Now, of course, they noticed it. Now, what did they do? They had a good solution. It was really kind of impressive. So they had a failure of their normal operational procedures. So they tried to fix it. It occurred to them that, well, they've got this NASA laser and LiDAR experiment right on board, and it was actually running kind of a shadow mode. They wanted to watch. It was new technology. They wanted to watch as it landed, test out to make sure it was working. So they said, well, why don't we just use that instead? And it turned out the data was accessible. They weren't programmed to do it, but the data was accessible. They knew they could get at it. It wasn't just a simple matter of switching data sources, though, because this thing shoots out 3 laser beams in different directions, so you can get estimates of your position in 3 dimensions. They were in a different location, and they're pointing different directions. So they had to do translations to account for the fact that lasers pointed different ways. So those are kind of straightforward matrix calculations, but they had to do it. The thing is, they did this from thinking of the idea. This was not a planned contingency. They just thought of it. And within one of their lunar orbits, which is 2 hours, they figured out what to do. They rewrote the software, with the extra translations and everything in there. So I think that was pretty impressive. They actually managed to accomplish that. So that was the really good news. The bad news is it didn't actually help. Man, the reason it didn't was that for some reason, the NASA data, they couldn't process it in real time fast enough. So actually, in reality, for the last 15 kilometers on the way down, which is about 12 minutes, they pretty much relied on inertial navigation. We've talked about that in previous meetings, but it's not very accurate, but it's the best you've got. But they do have cameras. And with optical navigation, what they can do, you look at 2 pictures successively as you get closer and closer to the ground. You look at a couple of features and they get wider. You can use a little bit of geometry pretty quickly to figure out, well, okay, we've now come down this much. Or actually what they did was they estimated the velocity based on that. And then knowing your previous altitude, you can guess what your current altitude is. So they did that on the way down. So they had no direct altimeter. It wasn't like they could just ask, hey, how high up are we? They had to do the calculations to do it. It wasn't very accurate. It turns out when they landed, they thought they were still 100 meters up. And that's probably why they had a bit of a rough landing. It wasn't too bad. All in all, it was amazing it worked at all. Now, they had a press conference where this is the CEO talking. He's got a little model of the lander here, and he's showing how the problem was when they landed, they still had some horizontal velocity. Normally, what they're trying for is to come straight down. You aim for the spot, you make your adjustments to get it right, and you just come down. If you've got horizontal velocity, you hit, you're just going to tip over. Which is what they did. And he's demonstrating that here. So they hit vertically, they're going about 6 miles an hour, and horizontally a couple miles an hour.
It hit the curve.
Yeah, and it hit the curve. So, maybe a rock, maybe a crevice or something, who knows. They've analyzed it now a lot more. And yeah, apparently they caught one of the little feet there. It got caught in a crevice or something. Luckily, it just so happened there's this little piece of blue plastic on the moon right there. You can see it, which kept it from tipping over any further. No, I'm kidding. He used that as a demo. Anyway, the point is, the landing wasn't really perfect. They were on a 12-degree slope, and that was interesting because their design actually only called for 10 degrees. So they actually were outside of design, and yet this was supposed to be an optimal landing site. It's a reminder that the moon is not really flat, and we need to keep that in mind. So they made contact after the landing, but the radio transmission was a lot weaker than they expected. And, well, the reason for that was the antennas were pointing the wrong way. But anyway, so they ended up about 30 degrees horizontal when all was said and done. So after you've landed, now what? The big issue is that the orientation is wrong. Very much like the Japanese lander called SLIM that we talked about last month. Same kind of problem. They rolled over all the way on their nose. At least these guys are only kind of sideways. It's sort of interesting. All the payloads are on the outside of the craft. It just so happens, just by luck, really, that the only payload that was actually facing downward on the ground was the art exhibit. So nobody really cared when you get down to it. All the other stuff could pretty much operate, except for there were some stereo cameras which are going to be looking at the dust, for modeling the dust and everything. I think they actually didn't work. It wasn't just because they're pointing the wrong way. There was some other problem they apparently had. But the real problem was the antennas. Some of them antennas were you have about 5 antennas at least, and some of them are unusable or at least not pointed the optimal direction. You're normally expecting, if you're vertical, you think you know where Earth is going to be. That was wrong. Unfortunately, the high gain antennas, the best antennas, were some of the ones that were way, way off. So that's why they were having trouble getting data, and it really cut into their data rates. So they didn't manage to transmit back anywhere near as much data as they'd hoped to. Now, the solar cells, that's the other problem area. This wasn't too bad. The ones that were on the very top, if you remember the original diagram of this thing, there were some solar cells on the very, very top. They were now on their side, but they're pointing away from the sun, so they didn't contribute much. But there were still those two panels that were on the normal sides, still produced quite a bit of power, so that they were okay there. So it's not as bad as the Japanese SLIM lander, which had been in a previous month, where they only had a couple of hours where they even had sunlight. Their solar cells were positioned so badly. They ended up transmitting maybe 350 megabytes of science and engineering data from all the payloads, which that actually isn't very much. You get down to it. I mean, you're talking, that's like, 10 high resolution pictures or something. So they had problems. The antennas are pointed wrong. They were limited on power, so they couldn't use their most powerful transmitter very long. They'd have to dip into the battery power pretty heavily to get that. And they had some other network problems too. So they didn't get as much as they wanted, but they did get some. So you can still say, well, they were successful that way. Finally, as the sun sets, they had to enter standby mode on February 29th. So they got basically a week of operations. They weren't able to transmit as much data as they would have liked, and they couldn't run all the experiments, but that got quite a bit done. Now, this does raise this question. We've now had two recent landers, the Japanese one I mentioned and this one, that both tipped over. Both of them landed on 10, 12, 14 degree kind of slopes. That's not going to be unusual. Actually, that was one of the points of the Japanese one. It was going to come down vertically and then purposely fall on its side. But the problem is it just kept rolling. So we're still going to have problems with that. In the South Pole, it's a messy area. There aren't that many flat spots. We don't tend to think about that. When you think of a rocket, you think of, well, what's SpaceX going to do with the Human Landing System? It's a huge thing. You notice the size of the people down here. It's a very, very tall rocket. That's not going to stand up on a much of a slope. They've really got to solve that problem. And these smaller landers are really kind of bringing out the problem. The Blue Origin one is kind of shrimpy by comparison down here, but at least it's kind of short and squat. It's probably a lot less likely to tip over, but this has been a reminder. And by the way, there was a third lander. There was a private one called the Hokuto R last year that also failed. And in a sense, it was because the programmers mentally were just sort of thinking the moon is flat. They forgot that as you're moving horizontally across the surface of the moon, when you go over a crater, all of a sudden it's going to look like you're a lot higher above the ground. And they forgot about that. So, it's little things that trip you up. It doesn't sound like much, but it's enough to wreck a mission. It definitely wrecked that earlier Japanese lander. Okay, there were some other minor controversies that come up. Columbia, the sportswear company, they have their name on this thing. In effect, advertising and also to do something useful. They use it as insulation. They needed to insulate those tanks, in particular the liquid oxygen and methane tanks. They used the same insulation that they use in their sportswear. I mean, literally the same stuff. I don't know why it's gold. Maybe there's a slight variation, but it's pretty much the same stuff. And that's good, though, because it means that they're thinking about what to do, and they're at least contributing, being a part of the space program, making progress. That contrasts to Patagonia, who actually very specifically has had an ad campaign saying, forget about Mars, let's not waste any time. And they're bringing up all the old tired arguments that, well, there's a lot of problems on Earth. Yeah, which is true, but there's always been problems. If we stop making progress in technology, every time there's a problem, we'd still be in the Stone Ages, or even the Polynesians never would have populated all the islands in the Pacific. It just wouldn't have happened if everybody said, oh, no, we've got a problem. Let's not do anything. That's just crazy. Well, also, of course, they're also forgetting that the only reason we know as much about how Earth works as we do is, in fact, that we have all this satellite-based monitoring going on. If it weren't for the space program, you wouldn't have much of an idea of so much stuff. You wouldn't have these nice pictures of the Arctic ice sheets. You wouldn't have temperature distributions throughout the atmosphere and the oceans. There's so much you wouldn't even know. And the other thing is that ultimately, to settle space, you have to master living in closed systems. It's just not going to be practical to constantly import everything from Earth. So you have to learn how to recycle everything. That's like a laboratory. It's hard to do it with the entire Earth. It's kind of hard to experiment on it, but on a much smaller scale, you're doing it. And we're just getting started on that. Biosphere 2 was probably the early, one of those well-known ones where they pretty much did try to throw in a huge portion of the Earthian ecosystems and see what would happen. But the point is, you will be making progress in these areas. The learning how to live in space is also the same thing as learning how to live on Earth. So I will not buy Patagonia clothing. I'm wearing a Columbia shirt right here. Okay, an update. I talked about the Japanese Slim lunar lander. This is the one that rolled over. That's a computer-generated image based on everything they know about their position. It's upside down. Anyway, it had landed and rolled over. The solar cells were pointing the wrong way. They pointed west. And on the moon, just like Earth, the sun rises in the east and sets in the west. So near sunset, they started getting solar illumination. So they got some power, managed to take some pictures and do some of the scientific stuff. But that didn't go on too long. You only had a couple of days to do that. And then they had to shut down for the night. And normally, just like the Nova C lander, they don't really design the electronics to survive the night. It's just too cold. It would cost way too much to really try to do that.
And the lunar night lasts
14. It's 14 Earth days, yeah. So you're not going to ride that out very easily. But it did actually manage to restart the next lunar afternoon. They actually had enough power. And in fact, they actually had too much heat. For some reason, they actually had too much. And so they had to be very, very careful not to overheat the equipment. But one of their main scientific instruments, a multiband spectroscopic camera, which they use for analyzing the rocks and the dirt and everything, that one apparently failed. But they're still able to get pictures and some of the other data. It's not functioning very well, but they managed to actually run even after living through one of those nights. And now they had to shut down again. And the next window they'll have is in March, and they'll get a few days. My guess is it'll be kind of zombie-like. Maybe you'll be able to communicate with it, maybe not, but it won't be very intelligible. That's just a guess. Think zombies. Another topic that we've covered in a lot of our previous meetings is the orbital debris problem, and most people have heard about this. There's a lot of satellites up there. There's dead ones. There's all the upper stages that got those satellites there. Many of them are still there. There's pieces of stuff that were blown up in anti-satellite weapons testing, just all kinds of stuff up there. I found this picture, which is kind of a nice one from the United Launch Alliance, highlighting the problem that as you're close to Earth, the low Earth orbits, like where the International Space Station are, they're 400 or 500 kilometers, that kind of a range. Satellites that are orbiting in that area, they can last in terms of years, 3 years, 10 years, somewhere in that range, depending on the altitude. And the reason is there's still enough air molecules up there that you get some friction. And over time, it gradually drags you down. But you don't have to get up much higher before you're off in the land where it takes centuries or even thousands of years. Those big old satellites that were used for satellite transmissions for television and that sort of thing, they're up in geosynchronous orbit 22,000 miles up. Those things will be there forever without special heat treatment. When they die, what they're supposed to do is raise those up even further to what's called the graveyard orbit. It's highlighted there on that picture. So anyway, that's highlighting the problem areas. So in a way, most of the congestion is down in low Earth orbit, but the good thing is that cleans itself out after a while anyway. But there's still enough of it that it's gotten to be a concern. So the reason we're talking about this is Astroscale, a Japanese company, has just launched something to do something about that. They're going to try to remove some, or at least they're going to study it. There is a dead upper rocket stage that's up there. H-2A was a Japanese upper stage. It was launched back in 2009. Actually, that's the same model rocket that took that Slim lander to the moon. 11 meters long, 4 meters in diameter, and weighs 3 tons. So it's a big chunk of metal that's up there. There's no communications possible with it. It's not powered. It isn't like you can tell it to move around. It's just dead. It's just up there. It wasn't prepared ahead of time. Some of the solution methods for dealing with space debris have said, well, okay, let's put special markings on things so we can identify places to dock or places to at least identify what it is. But none of that was done with this old stuff. So this is an attempt to figure out what to do with the old stuff. The biggest problem in all these things is they might be spinning. And if they're spinning, it's pretty hard to just grab it, which is what you want to do. You're going to grab it. Whatever craft you're in is going to start spinning too, and you may easily lose control. So anyway, Astroscale is the company. It's a joint project with the Japanese NASA, JAXA. It's a commercial removal of debris demo. What they're going to do is they're going to launch, and they're going to approach it. You can see in this picture here, the smaller one is the satellite they're sending up. It is actually quite a bit smaller than the rocket they're looking at. But all they're going to do is come near it. They're going to try to match the orbit and then actually circle around it multiple times and make sure that they can really get a good understanding, in particular to be able to show that you can match at least the primary axis of rotation. If you could do that, you've probably got a better shot at handling it after. This is only doing the observation. It's not actually doing any of the debris capture. It's not doing anything with it. They're just proving you can even do that. All these things are all baby steps, if you will. They haven't even contracted the next step, which is try to actually get this thing. But that's obviously what the intention is. The intention is to then grab this thing. A question came up about the future of the International Space Station. Well, that's the biggest piece of debris up there. Yeah, that's huge. That's such a whole controversy in itself. I can hardly even talk about that. Some people want to try to save it as a museum. Some people want to dismantle it. The obvious thing long term, which I'd really like to have, is a circular economy where you simply melt down this stuff and build new things up there and never have it come back to Earth. And if it comes back to Earth, some of it will just evaporate in the atmosphere, but maybe that's not such a great thing. You want to be breathing in aluminum ion, not necessarily a good thing. Anyway, so moving on, Varda Space, we talked about them in November. What they're doing is manufacturing in space, but this is manufacturing where you launch essentially a small lab, does crystallization kinds of things, in this case for biopharmaceuticals. And the reason you do that is that you can make much better crystals in space where there's no gravity, microgravity. Do a lot of different things you can't do on Earth. So they did this. They sent one up in June. It took them about 3 weeks to make the drug they were trying to make, and then they weren't allowed to land. They launched it in June. They were done by July, and they were waiting around. Finally, just this month, the FAA granted a re-entry license. Now, they also had to get approval from the military range in Utah where they were landing. All that stuff took time, but they finally got it, and then a week later they landed. We don't know the results yet. There's several kinds of results. One is they're sending the drug out to an independent testing lab to verify that actually it's the good stuff, no bad things happened. The other thing, they're actually making money. The Air Force is paying for information. They want to know more about hypersonic reentry. Things flying at 25 times the speed of sound when it's coming in. The Air Force wants that information. We'll probably never know what they find out, but we will find out about the drugs. Yeah.
The question came up, what is the drug ritonavir used for?
Well, apparently it was used for HIV treatments. But also, it's a part of Paxlovid, which is used for treating COVID. Paxlovid is a combination of ritonavir and some other drug, whatever it is. So the thing is, these are expensive drugs. Obviously, you're not going to make aspirin in space. It still costs you a lot of money to get up there and down. In their case, they send it up. You can see that on the left-hand side here. This little thing here in the middle, that's really the lab. They have a heat shield which heats up, and then eventually a parachute that drops, and they're landing on the land. This is the recovery right here. The point is they can reuse this thing, and they can get them up pretty quickly. So obviously they're going to start small scale. They want to get to the point where at least they fill up a Falcon 9 at a time. But for now, you start small because it doesn't cost as much. So here you're still demonstrating feasibility. They're doing another launch this year. There's a test. I think that third test they're hoping for this year, they're actually hoping to go commercial with it. And some of that will be landing on Australia. They have so much trouble getting approvals from the US that they're going to land on Australia. They still need FAA approval from the US because they're a US company, but at least they won't have any problem landing on a military test range.
The question came up, why didn't Varda get landing approval before they launched?
You might think they would have worked all that out. Something went awry in that whole process. Who knows? We'll never know the story on that. Okay, pop quiz time. Can you guess the country and the rocket? I blotted out some of the markings, logos and stuff. You can try squinting, but I don't think you're going to find any identifying names on there. Any guesses? Oh, you always know these things. Does anybody else know what this is? Okay, go ahead. You can say it.
I'm guessing Mars planet Long Island?
No. Actually, this is Japan. This is Taganashima or something. It's an offshore island of Japan. This is actually the H-3, which is the new rocket, replacing the one that just took that slim lander up there. This is still being owned by their NASA, built by Mitsubishi. They launched on February 16th. That was their first success. They had one previous launch that failed. Now, one thing that's kind of sad about this whole thing is that it's basically competing with the Falcon 9 and the Vulcan, which is the United Launch Alliance thing that just launched this year for the first time. It's expendable only. So basically what they're doing is they're competing with the Falcon 9 as it existed around 2010. They're finally competing with the 2010 version of the Falcon 9, not the 2015 version, which was when they started reusing the booster. And that's when things really started to get cheaper for SpaceX. By reusing the equipment, they can get the cost down. They can't do it. On the other hand, this thing is quite flexible. They can have either 2 or 3 engines. They're hydrogen and liquid oxygen. And they can have 0, 2, or 4 solid rocket boosters. This particular one has, they're little ones down here on the bottom. You can see them. This is the first success. So they're at least having something. They're managing to keep their rocket scientists employed. Actually, they think they can probably get pretty competitive with, strangely enough, with the Falcon 9. This won't be that much more expensive. I don't know why, actually, to be honest. These things will never be reusable. They have the same problem that the Vulcan has, the ULA one, which is that if you only have a couple of engines, you can't land the booster because it's too powerful. As soon as you turn it on, it just goes shooting right back up.
So it will always be expendable and probably more expensive.
I wouldn't laugh at them too much because they've done some of the best exotic kind of spacecraft. I mean, they're the ones that did the first recovery mission to sample an asteroid and bring it back. So they've done quite a few things with these kinds of launchers.
A question came up on where the Japanese are getting the hydrogen for this rocket.
I don't know where they get their hydrogen. Is it green? You're asking, is it green or electrolysis or,
There's that big body of water behind it. So that's
well, yeah, they do have water, but unfortunately that's loaded up with salt, which you electrolyze that, you get a lot of chlorine gas. This is, I don't know where they get it from, but this is just straight up liquid hydrogen, however they get it. Yeah. Okay, this is the last pop quiz item. Country and rocket. Okay, this one, I guess I didn't get any takers on this. Oh,
it's China. India. Long march.
Okay.
Sorry,
oh, you cheated. You looked at my next slide, did you?
Well,
Okay.
it just popped up. On March 7th, I was paying attention.
Countries, but it's not.
It's not China?
It's not China.
Well, he says it's not China.
Well, you're right.
All
I
right.
don't think it's Indian.
It's Indian. It's called GSLV. They don't have great names, but anyway, they are a geosynchronous satellite launch vehicle. This thing is, you were right, it wasn't China. They've had this since 2001. This is a pretty old rocket. This is not a new thing, but it just had a recent launch. They launched a big weather satellite. This is actually 3 stages, solid. It has a hydrazine liquid stage, which, immediately think toxic, horrible, you hate to be there. That's sort of left over. They got a lot of their early training. They pretty much picked up Russian technology, and the Russians always used hydrogen. Well, actually, so did we. Actually, everybody did. They kind of were in the Russian school of doing things, and that rocket was old, so they're still doing it. At some point, they will replace this. They are working on it. Okay, finally, we always ask at the end, how many launches have there been since our last meeting, which is about a month? Just take a guess. And by the way, this is the launch of that lunar lander on February 15th. Any guesses as to how many launches there were in the last month? Okay.
26.
Okay, that's a guess.
20.
You're a lot closer. Okay, the answer is 13 plus 4, 17. Actually, it's a little slow.
Oh, wow.
Yeah. That's funny to think about that. You go back a couple of years to think that 17 launches in a month is slow. But, actually, SpaceX even is falling behind. They were hoping for 150 launches on their own, just by themselves this year. They're going to have to launch like 3 a week to keep up, if they want to meet that target. They might not quite make it.
Yeah, they got 96 last.
Yeah. So this is really just, we can't go through all these, but gives you an idea of the kinds of things that are going on. There's a lot of satellites going up for communications. We've already talked about some of the Japanese test flight. We talked about the commercial removal of debris launch. And interestingly, that's not an Electron rocket, which is a very small one. But, they figured that was enough. I don't think I'll go through most of these. Crew to the International Space Station. SpaceX periodically launches a rocket that just includes a lot of payloads. They just basically bundled up. In fact, they don't even do the bundling anymore. There's third parties that come in and they will sell you a slot on a SpaceX rocket, a Falcon 9, and you pay those people and they bundle it up. They take care of the launching of it. Some of them have tugs. They have space tugs. So if you don't want to go to the orbit that SpaceX is going to, you get a little tug and they'll take you out somewhere else. And there's a couple of those in there. So there's more than 53 satellites. These are just the payloads, some of which have multiple satellites in them. So I think that's pretty much it. Yep, that's it.
Other space-related videos or slide presentations by me are available at the link shown here. That includes a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and a link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.